designed by artificial intelligence, innovative multi-physical system integrating smart material. From here, what I would like from you to memorize two keywords. First, the smart material. Second, the artificial intelligence. But before we start, let me tell you a little bit about my background. So what I have done is Master's in Fundamental Physics in Lebanese University. It has the third rank in Lebanon. Then I transformed to Sigma Clermont in France to get Master's in Mechanical Engineer, Innovative and Mechanism for Robotics. And now I'm currently involved in my PhD thesis with Pascal Institute and UCA as doctoral school. And those are my supervisors, Frederick Chappelle and Yuri Laposte. Now, going back to what we memorized at the beginning, the two keywords. Focusing on the first keyword, which is smart material. It is a good material science domain to integrated in engineering, robotic, biomedical fields. One of those smart material is shape memory alloy. Shape memory alloy, it's a raw material in many fields. Starting with its definition. What is shape memory alloy? First, it has a crystalline structure. Crystalline structure, it is a specific arrangement for the atoms or ions inside the molecule. The two main solid phases of this crystalline structure are austenite and martensite. Those two phases affected by external stimuli to temperature and stress. So we have two external stimuli that can affect the shape memory alloy to have a response as strain. So the two main stimuli are stress and temperature. Each one can define a characteristic for shape memory alloy. So what are the characteristics of shape memory alloy? They are two. Imagine this is the container of shape memory alloy. First characteristic, it has superelasticity. Second, shape memory effect. The main thing here to focus on is the temperature. Since at each range of temperature, we can define a characteristic. Between the temperature finish of the solid phase called martensite and the start temperature of the austenite phase, we can have the superelasticity. However, at temperature over the finished temperature of austenite phase, we have the shape memory effect. Too much details, okay, but they are important to follow next. So, to focus on superelasticity, it is when we apply a stress on shape memory effect, on shape memory alloy. This stress causes a transformation from one solid phase to another. So the shape memory alloy is going to deform, to has a displacement. However, for the second characteristic, yeah, we apply a stress, but here the main cause is the temperature. And this temperature doesn't lead to have a totally transformation in solid phase, but it is intermediate transformation from one martensite to another. But at the end, we have transformation, we have displacement. Okay? So we are talking about shape memory alloy. Its characteristic to superelasticity and shape memory effect. Okay, but why we choose shape memory alloy? Since shape memory alloy has several roles: sensors, linear actuator, rotatory manipulator, controller, self-centering, damping devices, etc. All these roles give a power for shape memory alloy to be used. Where can we find shape memory alloy? We found as sensors, as rings, wires, and focus on wires, reinforced concert beams, spring, and porous. Porous is the powder of shape memory alloy. So all these forms, we can find it in many applications in biomedical, robotics, autonomous, etc. But we are going to focus on biomedical and robotics fields since it is used as catheter tube or hard support device, sure, the artificial support device. And also in many applications for robotics that we have here. Now, shape memory alloy in general, let's go deeper. What is important for us as a researcher, how can we study shape memory alloy? There are three main methods: finite element methods, experimental machines, and computational methods. But all these are methods have high computational time, no real-time simulation, and low accuracy. All this disadvantage leads us to search for a new solution. And here, the second keyword exists, which is artificial intelligence can be a solution to study shape memory alloy with high performance. For that, we started to study the first characteristic of shape memory alloy, which is superelasticity. Under this topic, I had two publications. One is the review paper that has a contribution that each SMA role, SMA is a shape memory alloy, each SMA role and form of SMA can have one neural network to study. What we have chosen is a specific system of shape memory alloy called antagonistic system that can play an actuator role. And our role here is to find the proper neural network. First, let's define the antagonistic system. Imagine two single wires combined together at a midpoint. The edges are fixed. The exterior edges are fixed, but the interior are linked in a point. But this point is free, can move. Those two wires are linearly connected. A voltage applied at the voltage applied at the interior point, the midpoint of the two wires, and we have force sensor and displacement sensor to measure the stress that's coming from the force and the strain that's coming from the displacement. However, shape memory alloy is not that easy to apply voltage and measure the displacement, since it has a crystalline structure. So each time we need to apply voltage on one wire, heat it. Yeah, voltage leads to temperature. So we are heating the wire. We need to cool it again in order to reserve its crystalline main structure. Okay, so the cycle that we are going to work on is heating first wire in order to compress. So it elongates the second wire. Okay, then heat it by the voltage we apply it on. Okay, now we should cool it, not to deform it. There is no displacement at cooling, but only to reserve the crystalline phase. Okay, second, we are going to heat the second wire. It's going to compress the second, but elongate the first. This cycle should be repeated in order to have butterfly shape. When we study this cycle, theoretically, we have the linear shape, which is not that good, but it is okay. However, the experimental one is nonlinear. And here, the AI potential proved itself using a neural network to give a nonlinear result for this butterfly behavior. And the neural network here is the long short-term memory neural network with a regression layer. So yeah, we succeed to have this non-linear result using a neural network. We have done with the first characteristic. Now let's go to the second one, which is shape memory effect. This time we are going to focus on temperature displacement. What we have done first is stress, strain. Now temperature, strain. Okay. And this is what I'm doing, what I have started to do here at CETRIS. So we need to study how much is the temperature that can achieve an X value for displacement. Okay? Two ways. First, using artificial intelligence, which is now the reinforcement learning. And second, experimentally sure with theoretical simulation. I mean a numerical simulation, equations and values. And sure, here at the first point is going to have linear and nonlinear results. Starting with RL. So what is the task for RL to do here? We have talked a lot about materials. Let's talk in AI language. The RL here has a task. Please give me what is the proper voltage to apply on this SMA system in order to move 1 centimeter. Just imagine value. Okay? This is the task for the RL. RL can be defined by two things, environment and agent. In my case, the environment is the antagonistic system, the shape memory alloy system, and the agent is the Q-learning algorithm or method of the reinforcement learning. The environment is going to give the agent the displacement that it has initially, the reward that can be calculated referring to the target displacement, and now the agent should give the environment what is the proper voltage to apply on the antagonistic system. Those are the premier results that I have until now. It is the relation, the behavior. Also, it should be butterfly. The linear one shows us the simulation theoretically or numerically, and the relation between voltage and displacement. That's what I have done here, but this is not everything. I am also doing the electric circuit experimentally to get the result, and the numerical simulation was MATLAB code. But we are going to complete with that, hopefully to have a publication. Now, all this information, how can I use it to help the research field? Everything until now is just data. But where is the application? Yeah. Antagonistic system can play a role of actuator, which means can be an actuator for a finger, let's say. But I am focusing on biomedical field, and especially in the human brain field. So first, I need to prepare to study the proper environment for my application, which is a material mimics the human brain behavior. So I study its physical properties using many machines like rheometer, viscoanalyzer, and instrument machine that give the characteristic of stress, strain, and Young modulus. Second, I should study the biomedical properties of the human brain. For that, I focused on an operator called deep brain simulation. It's an operator to insert inside the human brain a small tube named as electrode inside the human brain, then remove it. But during this process, this material is deformed. According to the biomedical properties of the human, each part of this electrode has its specific deformation. Since there is a hypothesis said that human brain decomposed of 3 main layers, and each layer has its properties that can affect the electrode in different ways. What I have done focused on the deformation properties, which are 5, XYZ axis, and curvature and torsion for this deformed shape. So imagine this figure, it's the figure for deformed electrode. Again, using MATLAB and using reinforcement libraries of MATLAB, I have done clustering for this data. And I found, yes, the hypothesis validate using this code. I have found the 3-layer volumes with a centroid of each layer. Summary. So this is done starting from choosing the proper system, which is antagonistic system that play a main role in engineering field, robotic and biomedical, then study it theoretically to have a publication from it, then modeling it using a neural network, the first property, which is superelasticity, and control the second property using reinforcement learning, which is shape memory effect. All this information still need the environment to apply in, which is the human brain, or let's say material, mimic the human brain behavior, and at the end, I'm going to have this active device. So conclusion, deep learning, it's significant to model complex systems. Perspectives, we have neurosurgical application. Let's simulate the electrode after brain operation that I name it VPS. And soft robotic application, use deep learning for optimal design procedure, and at the end, linked application to intervent system integrating shape memory alloys. Thank you, and I'm available for your questions.
Thank you very much, Rodayna. Are there any questions in the public?
You don't like it?
Go ahead, yeah.
Very good one. The wings of the plane, during the flight travel, the plane travel, there are different stress values applied on the wings of the plane, yeah? But at each phase, we see at each value of stress and power and pressure, we can see that it deforms. Okay, there are many shape memory alloys in the plane of in the swing of the plane to decide the proper displacement at this stress in order to move the plane in the proper way. So this is one of the examples.
How is the cost viability of these materials? Like, are they very expensive to make, or are they cheap enough to be used in daily purposes or uses of materials?
Yeah, they are not expensive, but we still need to study more to be really, it's not easy to use. We need to really understand it well, prepare it well. There are many pre-procedure to do it on this material. It's not like an iron, we bring it and no, there's a crystalline structure. For that, we have a lot of pre-procedure to do.
Thank you, Rodayna. Are there any more questions here in the room? No? So let's see if in Teams. Yeah, go ahead. One more question.
The experimental data. Since at the beginning, I did experimentally the data to measure the stress and the strain using the sensors. After that, this is my data. I trained the neural network with.
Oh, okay.
And sure, I tested many neural networks, many main neural networks. But at the end, LSTM was the best one. If it is helpful for you or for your domain, there is a publication for this topic.
Okay, thank you. So let's see if in the Teams there are more questions. There is somebody having questions in Teams.
Pretty clear to me. Thank you very much.
Thank you, Roberto. We can hear you. Go ahead.
No, I said that I don't have any questions. Besides, I will have the possibility to interact with her tomorrow's meeting. So,
Okay, thank you, Roberto. Any more questions in Teams? No? So I have a question regarding the use of this antagonist device for example, this type of medical applications. How do you think that it could be useful? What type of actions we could do with this antagonist device in the brain or in other applications in medicine? And I think that the interesting thing is that you can deform this needle as you wish due to this material, isn't it? That's the advantage with regard to any typical needle based on some metal or some component that is not active. That's the good advantage, isn't it?
Cannot imagine what is the deformation that we have. But with shape memory alloy, yeah, we can know what is the deformation that's going to be inside the human brain, and we can see which dimensions of this system we can use in order to be in a safe side for this operation.
I remember being in a PhD defense done in Clermont about this electrode, and I was quite impressed about the fact that the brain is so heterogeneous, so many different materials inside the brain, and that you really need this deformation control of the needle in order to follow all the structures in the brain without creating damages. So I think that this is the good advantage of these materials, that you can control how this needle is deforming inside the brain. And in addition, you can also plan the path so that you cannot damage any part of the brain. And of course, the novelty, what I see in this work, from my previous experience with this PhD I was talking about, is that there are no active systems now in robotics that are able to have so many degrees of freedom to deform around the brain. So it's really a special application there where we really see the potential of these materials.
Just linear deformation. But if we are able to really control it well, we can increase the number of wires and it will be easier to study it. And for example, for my system, I started to study one single wire. Then from one single wire, I go to two linearly connected. So this is in progress. To reach many dimensions for deformation, I need to move from linear to 3D.
Okay, thank you. Yeah, more questions there. Go ahead.
Is vary from according to the dimension of the shape memory alloy. So I cannot say it's from X to Y, since it depends on the dimension that I have and on the phase that I have. And the form, yes. See, I have one material that is from -8 its martensite from -8 going to 68 as austenite. However, I have another one with different dimension, sure, which start from 58 until 79. So the range is, yeah, and this is only two examples. Maybe we have another example that have different ranges.
And so when you said that in some of the biomedical applications, you can use a needle that is made of the shape memory alloy that it can deform as we want. So I was wondering, maybe I was thinking that the temperatures are high, so we cannot use such temperatures when you're working on such sensitive parts. So that's why I was curious in knowing what are the temperature ranges to deform from one solid to a.
Yeah, according to what temperature we need, we can search for the proper dimensions.
Okay, thank you. Some more questions here or in Teams? No, so thank you very much, Rodayna.
Thank you, Prof. Juan. He was very kind with me. Really, you were so kind, so helpful. Thank you.
It's a pleasure to have you here.